All right, so we talked about in our last video that not every cyclic molecule that is fully conjugated, meaning that it has alternating double bonds, will be aromatic and have this aromatic stability, all right? In order for a molecule to be considered aromatic and very stable, that means it will not react readily, it must fulfill two very specific criteria. Okay, number one, we have to have a fully conjugated ring with overlapping p orbitals, meaning all of the atoms in the ring have to be sp2 hybridized. Okay, that's rule number one. Rule number two, we must meet Huckel's rule. This states that there has to be an odd number of electron pairs involved in the resonance. Okay, this means an odd number of pi electrons, where pi electrons are defined as either electrons in a pi bond, such as a double bond, or a delocalized lone pair. Right, so again, we're going to have to go back and remember, what does it mean for a lone pair to be delocalized? Okay, all right, so what if we have a molecule where criteria 1 is fulfilled, but not criteria 2? Meaning, kind of like we saw in our last video, we have a ring that has all sp2 hybridized atoms, but it has an even number of electron pairs, okay? We call these molecules anti-aromatic, okay? They're actually very, very unstable, the opposite of aromatic compounds, okay? Anti-aromatic compounds will have a fully conjugated ring with overlapping p orbitals and an even number of electron pairs, okay? So anti-aromatic compounds fulfill criteria 1, but not criteria 2 for aromaticity, okay? If you have a molecule that does not fulfill criteria 1, it's neither anti-aromatic or aromatic. Okay, benzene is our prototypical aromatic compound, but it is definitely not the only aromatic compound that exists in nature. So let's talk about some compounds that are aromatic other than benzene. For example, could we have a 5-membered ring that is aromatic? Well, in order for a compound to be aromatic, it would need to have an odd number of pi electron pairs, right? That means the minimum number of pi electron pairs would need to be 3, okay? 2 is an even number, and 1 is an odd number, but one set of electron pairs couldn't be in resonance with itself. We don't have enough, okay? A 5-membered ring can hold 2 double bonds, okay? Any carbon can have 1 double bond at a time. You cannot have a carbon that is in a cyclic structure and has more than 1 double bond, okay? So where does the third set of pi electrons come from? Well, we would need it to be a lone pair. We see that the hydrogen attached to a cyclopentadiene ring, this ring right here, is actually much, much more acidic than a typical sp3 hybridized carbon-hydrogen bond, because once that proton has gone and left a lone pair on this molecule, that molecule now will have 3 pairs of pi electron and will be classified as being aromatic. The lone pair that's left behind, and we'll go through this, will be delocalized and will be able to participate in resonance. Heteroatoms are also common to see as part of an aromatic ring. If a heteroatom has a lone pair that can be delocalized, it will count in Huckel's number of electrons, right? Now let's remember, in order for a lone pair to be delocalized, the atom it is attached to must have a steric number of 4 and must be right next to, adjacent to, a p orbital. Okay, that would mean either a positive charge on a carbon or a carbon that is double bonded, so it's sp2 hybridized and has a p orbital. We're going to look at pyridine and pyrrole as examples. Okay, the nitrogen on pyridine has a steric number of 3. So immediately I know its lone pair is not delocalized. Therefore, its lone pair is not counted when we count the number of pi electrons for Huckel's rule. On the molecule pyrrole, the nitrogen has a steric number of 4. It is also next to 2 sp2 hybridized carbons that have p orbitals. So its lone pair is delocalized and counts as part of Huckel's number when counting pi electrons. Okay. We can actually look at electrostatic maps that map out where electron energy is. And we can see that the electron density from the lone pair on the pyrrole is spread throughout the entire molecule, whereas the lone pair in pyridine is stuck right on that nitrogen because it is not delocalized. Okay. Again, this is a little tricky because we're going back and we have to remember about delocalized lone pairs. So Skill Builder 17.3 does a great job of walking you through how to determine whether or not a lone pair is delocalized.